Hello, everybody. My name is Shane, and this is my case study 6, the entity fraud investigation. So, in this presentation, we're going to be going over 4 different entities and investigating whether they are likely to be committing fraud based on Benford's law. And then we're going to be diving deep into a specific entity, which is a government entity, and it's a list of card transactions that occurred in the year 2010. So right off the bat, you're probably wondering, what is Benford's law? So Benford's law, also known as the law of the first digit, states that in many naturally occurring data sets, the frequency of the first digit of each number follows a specific pattern. Specifically, the law states that digit 1 appears as the first digit around 30% of the time, while the higher digits appear less frequently, with the digit 9 appearing as the first digit less than 5% of the time. Benford's law has been found to apply to a wide variety of data sets, including financial data such as tax returns, invoices, and stock prices, physical constants, population statistics, and scientific data such as the lengths of rivers and the masses of celestial bodies. The law is often used as a tool to detect anomalies of fraud or in financial data, since data that does not follow the expected pattern may indicate manipulation errors. However, it's worth noting that Benford's law is a statistical phenomenon and does not necessarily hold true for all datasets or all subsets of a given dataset. So you can see the image on the side is a good representation of what Benford's law typically looks like, and you can click the link for the image credit. So when we first look at the Sino Forest Corporation, this chart right here is a comparison of the Benford distribution and the Sino Forest Corporation's 2010 financial statement. When viewing the data from a glance, the data looks like it fits the Benford distribution well. There are a couple noticeable discrepancies among the distributions, such as the percentage of reports involving the number 8 being slightly larger than the distribution, and the percentage of reports involving the number 2 being slightly smaller than the distribution. We can dig deeper to see if the data fits the distribution using the chi-squared goodness of fit test. But before we continue our investigation, we're going to set our null hypothesis to having the statements consistent with Benford's law, and of course our alternative hypothesis being that the statements will not be consistent with Benford's law. To compute the test statistics for the chi-squared distribution, we need to use the following formula. So it's the observed values minus the expected value squared divided by the expected value, and of course the summation of all of the value pairs. And that is what our chi-squared right here, so we have the Greek symbol chi-square, our chi-squared test statistics going to be. Since we do not have the total count of the observed values, let alone the expected values, we can find that out using the Python programming language and the pandas library. We need to first group the data by each first number. After we have imported our data into a pandas data frame named Sino, we can group by using the .groupBy method like this. So this is taking the column named first, indicating the first integer of the transaction amount. The previous code block, of course, groups it, and we should have a data frame returned that looks something like this. The data frame does contain some redundant data in the last column, and we can remove that by using the .drop method like this. We now need to add the Benford distribution values. I actually have them contained in a separate list and added them to the data frame using the following code. When we look at, this first picture, it's 30.1%, 17.6%, and so on, and I do have that stored in a list. So now that's added to our pandas data frame, which we can use for an equation in just a minute. We can compute the expected value by multiplying the total amount by each distribution amount. So this can be done by using the following pandas Python lambda function, and I'll walk you through it just so it makes sense. So right here, we're creating a new column named expected, and it's going to be equal to the Benford column, and we're applying a lambda function to it where we take x, or the current piece of data we're iterating through on the Benford column, and we're going to multiply that by the total or the sum of all of the numbers in the number column of the Sino data set. So this is going to get us the total number of transactions, and we're multiplying that by the Benford distribution percentage, which is going to give us what the expected value should be with the amount of data in the set. As you would expect, um, let me read that over again. I thought that was kind of funny. The function above also stores that information into a new column named expected. As you would expect, please laugh, it contains what the expected value would be based on the total amount of data and the Benford distribution. Please laugh, seriously. I worked hard on that joke. I also created a function to help us easily find the test statistic for each data set. The function takes a clean data frame, the observed value column name, and the expected value column name. The function then computes the chi-square distribution test statistic, which is the equation that was referenced at the beginning of the last slide, so this one right here. Here's a function for reference. I built this on my own. Honestly, I don't know if there is one that I could have used, but this worked for me. So what we're doing is we're taking the data frame, observed value, and expected value as arguments. The O and the E are actually going to be referenced to the string that represents the column in the data frame right here. We first take a list, an empty list, and store it into the value chi totals. And then we iterate through each row, calculating that total. So like this equation right here, we're going to get the observed value minus the expected value squared divided by the expected value. And once we've iterated through every single row and calculated that value, we're going to sum all of the totals and create our test statistic. So summation of these calculated values, and then of course returning that test statistic. When we apply this function to the Sino data frame after it has been cleaned, we get a test statistic of 7.651. When plugged into this chi-square distribution graph generator found on statdistributions.com, with 8 degrees of freedom for the 9 numbers in the Benford distribution, we get the following graph. So our p-value is an outputted value of 0.468, which is actually pretty good for what we're trying to look for. When compared to our level of significance of alpha 0.05, and let me clarify, I know I didn't specify that at the beginning, but more often than not, your alpha value is going to be 0.05. And because the p-value is greater than it, we fail to reject the null hypothesis, since there is not enough evidence to suggest that the Sino Corporation's 2010 financial statements are not consistent with Benford's law. Thus, we can comfortably conclude that the Sino Forest Corporation is not likely committing fraud in their financial statements, and because of that, would not be worth our time investigating right now. Now that I've walked you through each step I took during my investigation of the Sino Forest Corporation, I'm pretty much performed the same steps for the remaining entities. So the government entity, the utility entity, and General Motors. And because of that, I'm not going to go in depth because I'm just repeating the same things I did for each entity. But unless I need to prove a point, I'm not going to go in depth. So let's look at GM. General Motors, when observing the comparison between Benford's distribution and GM's accounting, there seemed to be a few more discrepancies with several of the digit groups, which raised some questions regarding the validity of this data set. Before I continue, this data set is the amounts paid to vendors for the 90 days preceding General Motors' 2009 liquidation. So that's pretty important because in these situations, you typically find more often than not companies committing fraud or people on the inside trying to make some extra cash before the company goes under. Our first example is in digits 5, 6, 7, and 8. They're a little bit larger than their Benford counterparts, which is worth looking into, but especially digits 6 and 7, they're a little bit bigger than 5 and 8. And a little bit more concerning because of that size compared to their Benford counterparts. Like I said, it's not a huge amount, which we'll see in a little bit in a couple of the other investigations. Our second example is pretty much on the flip side, right? We see that the Benford percentage is higher in digits 1, 3, and 4. They are not significant, but small enough to notice. But as we know that not every data set will fit Benford's distribution perfectly, but they should be close. And it looks close, but we'll look into it. Our null hypothesis will be the distribution of the first digits of the amounts paid to vendors for the 90 days preceding General Motors' 2009 liquidation is consistent with Benford's law. And of course, on the flip side, our alternative hypothesis is that the amounts paid will not be consistent with Benford's law. When applying the function introduced in the Sino investigation to the General Motors data frame after it's been cleaned, we get a test statistic of 90.904. When plugged into this chi-square distribution graph generator found on statdistributions.com with 8 degrees of freedom, we get the following graph. Holy smokes, look at our p-value. P equals 0. The graph calculates a p-value of 0. When compared to our level of significance of alpha 0.05, we reject the null hypothesis since there is enough evidence to suggest that the amounts paid to vendors for the 90 days preceding General Motors' 2009 liquidation are not consistent with Benford's law, and we can conclude that there needs to be a deep investigation into the books of General Motors since there is a high likelihood of fraud that has occurred. Now let's look at the utilities. When observing the comparison between the Benford distribution and the division of a West Coast utility company's accounting, I noticed two concerns similar to when I was observing the distribution differences with the General Motors data set. So when we look at digits 1, 5, and 9, they are much higher than their Benford counterparts. And when I say much higher, I mean, of course, that's relative when compared to the other digits, but almost every other digit is less than their Benford counterpart, except digit 8, which is barely less. Because we're dealing with payment data, it seems like there's a lot more amounts being paid starting with 1, 5, and 9. And the comparison here seems less likely to fit Benford's data than General Motors', but again, we won't know until we perform our tests and analysis of the data. Our null hypothesis for this investigation is going to be that the payment data of the division is consistent. And then, of course, our alternate hypothesis will be that the payment data will not be consistent with Benford's law. When we apply the function introduced in the Sino investigation and ignore to the GM data frame, I mistyped that. It's actually the utility data frame. After it's been cleaned, we get a test statistic of hold your horses, buckle your seatbelts, guys, 4,335.98. Holy smokes. Yeah, there's something going on here. When plugged into this chi-square distribution graph generator, we get the following graph, and it's a p-value of 0, and the graph generator doesn't even give us a chi-value of greater than 500. That's how bad this distribution is. We absolutely have to reject the null hypothesis here, and we definitely need to do some more investigating. I'd argue even more there's a more precedent to do that than General Motors itself. Now we're going to look at the government entity that we're taking a peek at. And this is, like I said, of card transactions for a government entity in 2010. When observing the comparison between the Benford distribution and the card transactions for a government entity in 2010, I noticed a pretty big discrepancy in the data for digit number 3. Ignoring it, right, everything looks generally okay. I mean, a little less than their Benford counterpart. But when you look at digit number 3, it's almost 1.5 times more than its Benford counterpart. It's actually crazy. And because of that, we can infer confidently that there is a strong chance of fraud. But as we know, we won't know for sure until we investigate the data, and sometimes, and really not every time, data like this might not fit the Benford distribution. So we'll set our null hypothesis to the card transactions being consistent with Benford's law, and of course the alternate hypothesis having them not be consistent with Benford's law. Before we go on, here's a chart depicting the distribution of the last digit in transactions that occur for this government entity. Typically, you're seeing last transactions start or end with 0, 5, and 9, right? $100, $99, something 95, like 9.95, right? And those are expected, and it holds true for digits 0 and 5, but when we look at digit number 9, we actually see it falling behind digits, what's it called? Every single digit actually aside from 1, 3, and 6. Last digits can be interesting, but sometimes aren't a true tell of if fraud has occurred, but they can assist in a conclusion of fraud alongside other evidence. Um, like I said, typo right here, this should be government data, but when we apply the function introduced during the Sino investigation to the government data frame after it's been cleaned, we get a test statistic of hold your horses, buckle your seatbelts, 4,132.141. Not as bad as a utility, but pretty bad considering that there is this gap in data, which is almost blatantly fraud, but we get to look at it a little bit. Again, we get our p-value of 0, and the chi-value, or the test statistic doesn't even go higher than 500 in this chart. We, of course, have to reject the null hypothesis. There's enough evidence to suggest that the card transactions for the government entity are not consistent. Though the test statistic is not as high as the utility company, we can conclude that there needs to be a deep investigation into the books of this government entity and specifically look into the transactions that involve the number 3. Before I began diving deep into the government entity, I did a lot of data exploration. I probably spent 10 hours really grinding through this specific government data CSV. Because there's a lot of code involved in my investigation, um, like data science code, pandas, NumPy, SciPy, things like that, I won't be including any of it in the following slides. But if you are interested in it, please click this link to my Google Colab notebook. You're going to be able to view it. And if you want to run the notebook, you need to make sure you have the following files downloaded and stored um, in the notebook so everything works. If you don't, it's not going to work. It's going to have a bunch of errors. So make sure you have those downloaded with the correct names too. All right, so let's continue. After I cleaned the data and added a first integer column, I created a new pandas data frame to only contain transactions with the amount having 3 as the first number. The first thought I had when thinking as to how I would begin exploring the data was checking the number of transactions per merchant. When I ran some code to see what the top 5 merchants were, I got these 5 merchants. FedEx Ship 0AB, Staples, Office Depot, Sigma Aldrich, GSA FSS, ADV. And, without looking at that first merchant, I mean, these look pretty normal, right? So for the specific, um, or the number 3, I mean, several hundred, totally normal. It doesn't seem like a lot. The government spends a lot of money on a lot of things, has a lot of transactions. But when we see this first merchant, 8,238 transactions. That rings a bell. Let me tell you. It had almost 41 times more transactions than the merchant with the next largest number. That's actually crazy. I mean, I thought it could be a coincidence since the government does contract with people like FedEx and UPS to help deliver packages for the U.S. Postal Service when they're swamped, but 8,238 transactions? That's I don't know. I think that's a lot. So just to make sure, I took a look across the entirety of the data by integer for this specific merchant, and I created the following chart to give you guys a good visualization of what's happening here. So we see that among all first digits with this specific merchant, and this is the amount, so like paying $300, $400, $500, or whatever, right? Whatever that first digit is of the transaction amount. I mean, there's no competition here. There is over 8,000 transactions, starting with the number 3, and the closest one being the number 1, which is what you would assume would be. This is extremely concerning. Um, because of this super strange distribution among the first integers in this merchant's transaction data, my next thought was to see if there was a specific time of the year the merchant conducted transactions, because we could see, like, are they all lumped in a specific month? And if there is a large concentration of like transactions, we can also assume that there's fraud taking place and have more evidence against this merchant, or at least can help lead us to figure out what is all happening here. So let's move on. When we graph the distribution of transactions amongst the year of 2010 for the FedEx Ship 0AB merchant, we get this super interesting visual. So we see that there are a lot of transactions happening this year, and then only 2 transactions happening in October. You can't even see it. Looking at the data frame that I generated for the year of this merchant, in the month of October, there are only 2 transactions, while the next lowest amount occurs in November with only 101 transactions. That's absolutely insane. And, when we look back here, this is over the year, okay? 274 transactions for Staples over the year, right? We had just 101 for this FedEx merchant just in November alone. Of course, that amount pales in comparison to the largest number of transactions, which occurred in October with a total of 1,409 individual transactions. So from here, I thought, okay, best step would probably be to investigate the transactions that occurred in the month of October. And when we graph the number of or distribution of transactions by day, we get another interesting visual. You might notice that there's a couple days missing, like the 2nd, the 4th, the 6th, and so on, the 12th. And those are transaction dates that actually had no recorded transactions. So we can assume that there's 0. For the sake of this graph or chart, I didn't include them. I only included dates that had transactions. So right off the bat, several things stick out from the data. First, there's only 1 transaction on the 11th and only 5 transactions on the 17th. Everything else, tons, right? On the other hand, top 3 highest number of transactions occurred on the 10th with 172, the 20th with 150, and the 14th with 144 transactions, which is crazy. Who's swiping that card 172 times during the day? With that in mind, I thought the next best step from here would be to investigate the 10th of October, since it's the most, to see if there's any discrepancies in the data that could help us determine if fraudulent transactions are taking place. Before I went looking to see if there were any duplicate transactions, I wanted to look at the different card numbers used that day. When graphed to get the following, when we graph it, we get the following visual, which is actually absolutely crazy. These 5 cards right here were only used once. I want to make that very clear. They were only used once with this merchant that day. Okay. This one was 2. This one was 3. These ones are like 10 and 12, right? And then we have, I want to say 135 transactions with this one card. So card number 51422977710. It was used over 125 times that day. So aside from the concerning amount of cards usage for that particular card, the amount shadows the other 7 cards by so much. And with this in mind, we now can look at the card number, unique transaction amounts. And if we see a lot of the same dollar amount, it would further confirm my suspicions that fraudulent transactions are occurring with this merchant, or at least with the card number. And when observing that, we get the following visual. And this one actually blew my mind because, okay, you're swiping your card 100, let's just say 125. I know it's more. 125 times with this one merchant. And it's FedEx, right? So you're shipping something probably. Are you really spending $362 over 90 times? That's a little fishy. On top of that, $367 over 20 times. These are unique transaction values. They're not around it. The individual spent $362 over 90 times on October 10th. They spent $367 over 20 times, almost 25 times on October 10th, and $357 almost 20 times. With those 3 unique transaction amounts, this is extremely conserving. Because what costs $362 and needs to be charged almost 100 times in a single day? I highly doubt the individual with this card is shipping the exact same box almost 100 times. In conclusion, there needs to be immediate action on the following items. Number 1, investigate the merchant FedEx SHP 0AB and the transaction amounts taken place over the year 2010. Look for repeated amounts and look into why this merchant had only 2 transactions in the month of October for 2010. Second, investigate the cardholder of card number 51422977710. Are they having duplicate transactions with other merchants? What exactly are they purchasing that warrants almost 100 duplicate amounts on October 10th, 2010? I hope you enjoyed watching my investigative analysis on these entities, especially the government entity listed in this data. I spent a lot of time on it and scratching my head to get this data. And I hope you learned something too. Have a great day, and yeah, bye.